Welcome viewers. In this video, we'll see the definition of divergent theorem, Laplace and Poisson equation. First, we'll see the divergence. So, this divergence is defined as the net outward flow of the flux. Net outward flow of the flux per unit volume over a closed incremental surface. Right? So this divergence, what is defining? Outward flow of the flux per unit volume, flow of flux over a closed incremental surface. So that is given by divergence A equal to limit del V tends to 0, the volume tends to 0, surface integral, this is double integral, A dot ds divided by dV. So this is nothing but is a flow of flux in a surface area divided by volume. So that is the definition given, right? Divergence A equal to limit the volume tends to 0, the surface integral of A dot ds divided by dV, net outflow of the flux per unit surface divided by volume, right? So this del A can be represented as del dot A, right? This also this symbol is del, right? So we'll go into the del operator. So it is given as so dou by dou x plus dou by dou y plus dou by dou z. It's a partial differentiation. The del operator is nothing but a partial differentiation. In that, there are three types of coordinate system available. Cartesian coordinate system. If it is Cartesian coordinate system, it is dou ax by dou x, dou by dou y, dou by dou z. Right? In case of del A is given, it is partial differentiated with dou x, dou y and dou z, because in Cartesian system we have three parameter x, y and z. While going with a cylindrical coordinate system, the same thing what we have r, pi and z, right? R, pi and z. So that dou by dou r, dou by dou pi, dou by dou z, right? So this dou z and dou r, these two are length, but this dou pi is the angle. So that in order to make it into equivalent, it is divided by 1 by r. So this also become the length equivalent to the d pi, right? This is the length parameter, this is the length parameter. In order to make this angle into equivalent length, so that all will be equivalent length, so that it is multiplied by 1 by r. While going with a spherical coordinate system, it is represented by r, theta and pi, right? Dou by dou r, dou by dou theta, dou by dou pi. This r is the length parameter, but theta is angle, so that it is multiplied by 1 by r. Similarly, pi is also length, so it is multiplied by 1 by r sin theta. So that this will be length, this will be length, equivalent length to d theta, this will be equivalent length equivalent to d pi. So all three become a length parameter, right? So in Cartesian we have x, y, z. In cylindrical we have r, pi and z. In spherical we have r, theta and pi, right? So that we can find the del operator using any one of these coordinate system. Now we'll see the divergent theorem. From the divergent definition of divergent, we'll go to the divergent theorem. So what is given is a double integral, surface integral A dot ds equal to triple integral, volume integral del dot A into dV, right? So the divergent theorem gives relating the surface integral to volume integral, double integral to triple integral, right? What is the definition given? The line integral of the normal component of any vector field over a closed surface. So this is the line integral of the normal component of any vector field over a closed surface is equal to integral of the divergence of this vector. This is divergence of this vector throughout the volume enclosed by that closed surface. So volume enclosed, this is a surface, this one is a volume enclosed, right? So any vector field surface integral is equal to divergence of that equivalent field in a closed volume surface. closed volume, right? Relating the surface integral to volume integral, right? This is the theorem, statement of the divergence theorem. Now we'll go to the proof of this. So in this proof, first we'll start with the divergence. The divergence of any vector A is given by, what is that? Del dot A equal to dou AX by dou X, dou AY by dou Y, dou AZ by dou Z, right? Here we are using the rectangular coordinate system, right? Del dot A, that is nothing but divergence of A. Now multiply with the volume integral, triple integral, because in the divergence theorem it is relating volume integral to surface integral. Okay, so we start with the divergence. Now we are multiply with the triple integral on both the side. So triple integral del dot A dv equal to triple integral this factor dou x, dou y, dou z. Because of triple integral we need to integrate with respect to dx, dy and dz, right? First we will consider the x direction. Consider an element of volume in x direction. Then we'll go to y and z. First we will consider only x direction, right? So triple integral dou ax dou x into dx dy dz, right? We consider only this parameter in the x direction, right? So that is equal to double integral. So this alone is written as a single integral, right? Because first we need to integrate with respect to x, then y, then z. So we are considering this. So that double integral of is inside integral dou ax by dou x into dx, dy dz. So first we consider the x parameter. What is dou ax by dou x into dx? These two got cancelled, only we got ax, right? Ax into dy dz. So then what will happen? Dou ax by dou x dx dy dz is nothing but double integral. Now this triple integral is reduced to double integral ax dou y dy dz. So that can be written as ax dsx. What is sx? X means y into z. The x represent the y coordinate and z coordinate, right? So this entire x direction can be represented as ax into dsx, right? Similarly we can go for the other is given here, where dy dz equal to dsx, that is surface area normal to the x direction, right? Now we got the value for x direction. Similarly we can calculate y and z direction. So similar to x direction, the y also can be written as dou ay by dou y into dx dy dz can be written as the surface integral. Now that triple integral is reduced to surface integral ay dsy. Previously what we have? Ax dsx. Similarly y means ay dsy. Similarly for the z direction az dsz, right? Now we got all three, ax, ay, az from equation 1. This is equation 2 and 3, right? So from all these three equation, this side is triple integral v del dot a dv equal to, so from equation 1 and 3 we can write this ax dsx plus ay dsy plus az dsz, right? We can now see this triple integral is equivalent to this double integral, surface integral, right? So the entire thing can be written as a into ds. The ds is a normal. Ds means either xy, yz or zx. So that can be written as a ds, right? So triple integral, volume integral del dot a dv is nothing but double integral a dot ds. So that is the statement given by the divergence theorem. That is, the divergence theorem converts the surface integral into volume integral provided that closed surface encloses certain volume, right? It converts from volume integral to surface integral for a closed surface. Now we'll see Poisson and Laplace equation, right? We start from consider a Gauss law in point form, del dot D equal to rho V. Right, we start from this, the expression del dot D equal to rho V. You know that D equal to epsilon E. So that replace this D as epsilon E. Right. So del dot epsilon E equal to rho V. You take this equation number 1. But E equal to minus del V. Another relation is available. Electric field intensity equal to negative of the potential gradient. E equal to minus del V. Right. Now we substitute this E in this first equation. So del dot epsilon, here we are substituting E as minus del V equal to rho V. So what will happen? This epsilon is taken outside, minus epsilon. So del dot V equal to rho V. So that is nothing but del square V minus epsilon del square V equal to rho V. Right. So that can be written as del square V equal to minus rho V by epsilon. Right. After simplification, what we got? Del square V equal to minus rho V divided by epsilon. So this is nothing but a Poisson equation. This equation is represented as Poisson equation. Right. In this Poisson equation, if the volume charge density is 0, that is, there is no charge is available, the rho V is 0, then it is true for dielectric medium, then this equation become Poisson equation. The Poisson equation become like this, del square V equal to 0. Right. So in this above Poisson equation, if the charge is 0, that is nothing but dielectric medium. The charge is 0 means a dielectric medium, so that Poisson equation become del square V equal to 0. The charge is 0. So this equation is represented as a Laplace equation. Del square V equal to 0 is nothing but a Laplace equation. Welcome viewers. In this video, we'll see the definition of curl and the Stokes Theorem, statement and proof. First we'll see the curl. The curl of a vector at any point is defined as the limit of the ratio of the integral of its cross product with outward drawn normal over a closed surface to the volume enclosed by the surface as volume tends to 0. So this is a definition given by the curl. So that curl is nothing but limit volume tends to 0 1 by V double integral surface integral n vector cross f vector into ds. Right. So the curl of f is nothing but the volume is tends to 0, right, 1 divided by V n vector cross f vector into ds double integral. Right. So that is the definition given here. The cross product of the outward drawn over a closed surface to the volume enclosed. So that is divided by V. Right. So this is the expression for curl. This is the vector point function, and it is also referred as del vector del cross f vector. Right. The curl expressed in another way is del cross f vector. So this del cross f vector is represented as I vector, j vector, k vector. First row. Second row is dou by dou x, dou by dou y, and dou by dou z. The third is fx, fy, and fz. Now we'll see the Stokes theorem. The Stokes theorem, first we'll see the statement. The line integral of a vector around a closed path. So this is the line integral f dot dl. The line integral of vector around a closed path is equal to the integral of normal components of its curl over any surface bounded by the closed path. Right. So this is a double integral, surface integral of a curl of vector in the normal component of surface is nothing but the curl. Right. So it is equal to line integral of vector around a closed path is equal to surface integral of curl in a normal surface. That is the statement given in the Stokes theorem. Right. Now we'll see the proof of this Stokes theorem. So consider this segment is available, surface area S is available. right? It is split into so many small parts. This 1, 2, 3, 4, like that n number of parts are available, right? So S is the surface area that is divided into so many segments, smaller elements. That is, in this diagram it is available 1, 2, 3 and 4, right? Now we'll see this. Consider a surface S, right? We consider the surface S. F vector is a field vector, right? We consider one field vector. From the definition of the curl, it is curl of F equal to limit S tends to 0, surface tends to 0, pi into F dot dl by S. So this is the definition from the curl, right? Now we consider one surface that is split into so many elements. F is the vector. Based on the vector, from definition of the curl of F is nothing but limit surface S tends to 0 by F dot dl divided by S. You take this equation number as 1. Now divide the area S into larger number of smaller elements 1, 2, 3, 4 up to etc. Right? So we are having the area S that is split into small elements, large number of small elements, right? In our diagram we shown 1, 2, 3, 4. 4 elements are available. So from this, based on the small elements, from the diagram we can write integral F dot dl equal to integral F dot dl1 plus integral F dot dl2, like that. 1, 2, 3, 4, it will go like this, right? Now the big element is converted into smaller element, large number of smaller element like 1, 2, like that, dl1, dl2, like that, right? So from equation 1, F dot dl equal to curl of F dot S, right? That is the given from the equation 1. So by take the differentiate on both the side, so this integral become normal, F dot dl. So while differentiating this side, what we got, curl of F equal to S become ds, right? So we are differentiating on both the side so that this expression become normal, F dot dl. Already one integral is there, while differentiating it become normal. While differentiating this element, it become ds, right? So now we can replace F dot dl equal to curl of F into ds, right? This is for one element. Like that, while considering the n number of elements, integral F dot dl equal to curl of F dot ds1, curl of F dot ds2, like that. There are n number of surface available. So in general, we can write integral F dot dl equal to double integral curl of F dot n vector into ds, surface integral, right? So by now first we consider the surface area, then split it into n numbers. From the n number of elements, we got this expression. So the Stokes theorem is proved. So in this video, we discuss about the definition of curl, Stokes theorem, statement followed by the proof. Thank you. Welcome viewers. In this video, we'll see the definition of current and current density. First, we'll see the current. So the current is defined as flow of charges per second. That is nothing but I equal to minus dq by dt. Rate of flow of charge per unit second. dq by dt is nothing but the current. Current flow is defined as the flow of charges, right? So this negative sign indicates the direction of conventional current is opposite to the electron current, right? That is indicated by this negative sign. So I equal to minus dq divided by dt. Rate of change of charges is nothing but a current. Now we'll see the current density. What is current density? Normally the current density refers either length, area or volume. Here we are referring the area, right? So why we are going for current density? Suppose if a steady current is passing through a conductor, the current density is uniform if conductor has uniform cross section, right? If a steady current is flowing through a conductor, if the conductor cross section is uniform, then the current density also uniform, right? Suppose if the current density will be different at different points, if the cross section is non-uniform, If the conductor cross section is not uniform, then current density also not uniform. It will differ from point to point, right? So based on that, so we can define current density. Current density is defined as the current flowing per unit area when the area is held normal to the flow of charges, right? So if the cross sectional area is uniform, current density also uniform. If the cross section area of a conductor is not uniform, the current density will different, right? So based on that, it is defined as current flowing per unit area. We are assuming that area is held normal to the flow of the charges, right? We'll see the definition. So current density J equal to di divided by ds, right? Current density J equal to di divided by ds. Current per unit area, right? Cross multiply these two, so that dI equal to J into ds, right? dI equal to current density into ds. By integrating on both sides, we'll get I equal to integral J dot ds. Is surface integral, double integral, right? So the current expressed in terms of current density S, I equal to surface integral J dot ds. Now we'll see the conduction current. What is mean by conduction current? So this conduction current is nothing but normal current flowing through any conductor is the conduction current. It is the current flowing through a conductor whose resistance is R, right? The current what we are normally referring is a conduction current. It is flowing through a conductor with resistance R. Suppose if the potential V is applied across the conductor, then the conduction current IC equal to V divided by R, right? The potential V is applied across the conductor, the resistance of the conductor is R, so that the conduction current IC equal to V divided by R, right? So the conduction current is the normal current what we are referring flowing through the conductor with resistance R with applied voltage V. From this, the resistance of the conductor is given by, I will take this equation number 1. The resistance of the conductor is R equal to rho L by A, resistivity. In terms of resistivity, R can be replaced as rho L by A. This rho is resistivity, L is the length of the conductor, A is the area of the conductor. So while going into conductivity of the material, conductivity sigma is nothing but 1 by rho. Both are inversely proportional, conductivity and resistivity, right? So based on this R can be written as R equal to L by A. This rho is now replaced as 1 by sigma, right? This is not a rho, this is sigma. Now R can be expressed as L divided by sigma A, right? Now we can replace this R with this value. Similarly, the V. If E is the potential, E is the electric field intensity in a conductor, the potential V is given as V equal to E dot L. Normally the E equal to V by L, so that V equal to E into L, right? Now we got the expression for potential also in terms of electric field intensity, right? So the equation 1 is available here, IC equal to V by R, right? So the R we can represent it as L divided by sigma A, conductivity, right? The V represented as E into L in terms of electric field intensity. Now we can replace these two. So the equation 1 is nothing but IC equal to V divided by R. V is E into L, R is L by rho A, right? So that L got cancelled. So E into rho into A, right? So IC can, this is rho. Sigma, not a rho, is a sigma. E sigma A, right? So the conduction current is expressed in terms of electric field intensity, then conductivity and area of the conductor. IC equal to E sigma A. Now we'll see the displacement current. So in the displacement current, this current is nothing but current flowing through a capacitor when AC voltage is applied across the capacitor. So the conduction current is nothing but current flowing through any conductor with resistivity R and voltage V. The current flowing through the capacitor is named as displacement current, right? When AC voltage is applied, the current is flowing through the capacitor is nothing but displacement current. ID equal to dq divided by dt, right? So the displacement current can be expressed as dq divided by dt, right? But q equal to cv. This q is replaced as c into v, so that id equal to c into dv by dt, right? Now it is replaced as c dv by dt. From parallel plate capacitor, the C, the capacitor expression is epsilon A divided by D. Right? A is nothing but area, D is the distance between the plate, this permittivity. Right? So now we will replace this C with epsilon A by D, so that ID equal to epsilon A divided by D into dV by dt. Right? Now we have one more expression is available, E equal to V by D. E equal to V by D, so that we'll replace this. So E equal to V by D, so this V by D, this dV by D is replaced as E, right? So that E equal to V by D. And one more expression is there, epsilon E. Epsilon E is nothing but displacement density D, right? So this epsilon E is now replaced as D, right? So we have epsilon C equal to epsilon A by D is replaced. After that, V by D is replaced by electric field intensity. Epsilon E is replaced by displacement density. So finally what we got, ID equal to A dd divided by dt, area into differentiation of displacement density, right? So the displacement current is nothing but current flowing through a capacitor, right? Now we'll see the convection current. So the name is given, convection means it is distinct from the conduction current, does not involve any conductors, and also it will not satisfy the Ohm's law, right? Convection current means it is completely different from conduction current, right? It will not, does not having any conductors, and also it will not applicable for Ohm's law, right? Then what is that convection current? It occurs when the current flows through a insulating medium such as liquid or vacuum, right? Without the conductor, it is flowing through a liquid or vacuum, then it is called a convection current. It does not flowing through any conductor, not satisfying the Ohm's law, right? So in this video we discuss the definition of current, then current density, conduction current, displacement current, and convection current, right? These topics are discussed in this video. Thank you all.